Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Network Intelligence at the ECE and RBCCPS IISc. It's my pleasure to introduce today's speaker, Professor Arghyadip. He will be speaking on adapted multi-armed bandit algorithms for Markovian and i.i.d. rivers. Professor Roy received his PhD degree in electrical engineering from IIT Bombay in 2019. Before that, he received the BE and MTech degrees from Jadavpur University and IIT Kharagpur respectively. He worked as a postdoctoral researcher at the University of Illinois at Urbana-Champaign, USA from 2019 to 2021. He is currently working as an assistant professor in the Mehta Family School of Data Science and Artificial Intelligence at IIT Guwahati. His research interests include resource allocation in wireless networks, optimization, and control of stochastic systems and reinforcement learning. Before I move on to the talk, we would like to request the audience to subscribe to our Google group for information on our future talks. You can also visit our website for more details. I'll be pasting the links on the chat box. Please do check. Finally, we request the audience to keep your microphone silent for the duration of the talk, except when asking questions. And for questions, feel free to unmute yourself and ask directly or type them in the chat box. We'll relay your questions. Over to you, Professor Roy.
Thanks a lot for the kind introduction and thanks for the invitation. So, should we start?
Yes, please.
So, I'll just share my screen. Is it visible?
Yes, it's visible, but it's not full screen.
Now?
Yes.
Okay. So, today we'll be talking about, just a second. Today we'll be talking about adaptive multi-arm bandit algorithms for Markovian and i.i.d. rewards. This is a joint work with Professor Sanjoy Sagotai from UT Austin and Professor R. Srikanth from University of Illinois at Urbana-Champaign. So this is the outline of my talk. First, I will talk about some introduction and followed by the related work. And then I will talk about the TV KL-UCB algorithm that we have proposed in this work, followed by the regret upper bound and conclusions and future work. So there is a fundamental trade-off between exploration and exploitation. Okay, so this is a fundamental trade-off in decision making. For example, when I say the term exploitation, it basically means that you choose the best action given the current knowledge. So you have a current knowledge about a system where multiple options are available to you, and based on your current knowledge, you are trying to exploit the best action or best option that is available to you. This is called exploitation. On the other hand, there is something called exploration, which is basically allowing the system to gather more knowledge and try to explore on all the other options which may not be good looking to you at the current point of time. Okay, so there is a fundamental trade-off whenever you try to learn something. There is a fundamental trade-off between exploration and exploitation. For example, let's consider that you have visited a new city and you are going to stay there, and you want to find out which is the best restaurant in town. Okay, so what you will do is, let's say you visit some of the restaurants, and then based on that knowledge, you try to go to the restaurant. You keep on going to the restaurant which is the best so far according to you. So if you do that, then it's called then this is called exploitation, because basically you are exploiting the current knowledge about the restaurant. But on the other hand, what you can do is, although some of the restaurants which may not be good so far, you can keep going there just to make sure whether in future your experience might be better, and you may eventually end up liking it. Okay, so this is the dilemma when you try to when you try to find out the best restaurant in town. Okay, so either you can keep going to your favorite restaurant, which is basically sort of exploitation, or you can try a new one where you have not gone, or try in one where you have not gone many times. This is called exploitation. Similar situation arises in online advertisement also. Okay, so for example, in a setting where you are shown a set of advertisement, and the goal of the agent is to maximize the probability of you clicking on one of the ads. Okay, so now what will happen, if you click on a particular ad, the agent might end up showing you those kind of ads repeatedly. That is like an exploitation from point of view of the agent, or the agent can go for another type of ad and try to see what kind of reaction you give. Okay, so this is also another scenario where this exploration versus exploitation dilemma is there. Okay, so this kind of problems where this kind of exploration versus exploitation dilemma is there, I mean, this kind of problems can be modeled as a multi-arm bandit problem. Okay, so in a multi-arm bandit problem, what you do is you choose arms sequentially from a set of arms. Okay, so there is a set of arms which is like a set of options available to you, and you need to choose the arm sequentially from that set, and each arm produces certain reward. But the problem is the statistics of the reward distribution is unknown. Okay, so each of the arm is throwing you some stochastic reward, but the problem is you don't know what is the statistics. If you know the statistics, probably you'd be able to figure out which is the best arm in an expected sense, expected mean reward sense. But the problem is the statistics is in the learning framework, the statistics of the reward distribution is unknown to you, but your goal is to maximize the total expected reward. Okay, so you want to maximize your reward, but the problem is the statistics of the reward distribution is unknown to you. Okay, so this is the dilemma, and equivalently we can also talk about something called regret, which is basically you can say it's like the difference between the best solution minus so reward obtained under best solution minus the reward obtained under your solution. So maximizing the total reward is basically same as minimizing the total regret. Okay, so in Bandit, actually, this regret terminology is more common, so we use the term regret. But both the objective are basically similar. Either you want to maximize the total reward or total expected reward, or minimize the total expected regret and total regret. Those two things are equivalent. Okay, so traditionally this stochastic reward framework, stochastic multi-arm bandit, can be classified into two categories. One is called i.i.d, where the rewards are generated from some i.i.d process, independent and identically distributed random variables generate the rewards. Or it could be Markovian, where there is a temporal dependence on the rewards generated from a particular arm. So in this case, what can happen is, let's say there is a concept of state, where let's say there are state 0 and 1. So it's a two-state Markov chain, and then depending on whether you are in state 0 or you are in state 1, the reward that you get, the underlying distribution can change. Okay, so this is the Markovian model. So under Markovian, there are two categories of multi-arm bandit. One is called rested multi-arm bandit, another is called restless. So in a rested multi-arm bandit, what happens is the state of the arm is frozen when it is not played. So let's say there are 10 arms. If I have chosen arm number 5 at the current iteration, then if I don't choose it till iteration number 50, the state will be frozen. The state of the arm will not change. Whereas in case of restless multi-arm bandit, the state of the arm can change actually, irrespective of its selection. In the state of the arm can change. So this is more difficult to handle. In this work, we will talk about the rested setting, where if you play the arm, then only the state may change. Otherwise, it will be frozen. Okay. So any doubts so far? Okay. So let me give you some more motivations behind why this kind of models are useful or worth considering. So if you consider a casino where different kind of slot machines are there, and then what you can do is you can formulate a multi-arm bandit problem in this setting, where basically you go to the casino and then try pulling the levers of these different slot machines and get a stochastic reward. Now, if you get a high reward in the current play, then the probability that you will get a low reward in the next day is very high. Generally, if you win by choosing by pulling a lever, the next time you win, that probability is typically low. Okay, so in this case, there is a sort of a temporal correlation between your rewards, right? So what rewards have you have got in the last selection, that basically has an impact on the reward that you are going to get in the next time. So there is some sort of some form of temporal correlation. Similarly, in case of like this IMDb TV, like this movie recommendation system. So in movie recommendation system, what happens is the recommender will show you some sort of movies. Let's say initially the list will be very random, and then based on your choice, let's say you watch a horror movie. So next time it will try to show you more horror movies or a combination of horror and thriller movies, so that the probability of you picking a movie is more. So why that is happening? Because there is some sort of some temporal correlation on your selection also. Because today, if you select a horror movie, there is a chance that tomorrow also you might like another horror movie to watch. Okay, so so there is a temporal correlation of the user selection in this case also. Similarly, in case of medical trials, the result obtained by a particular medicine could be very much correlated to its earlier result. So all this, like all these kind of use cases motivates us to consider the correlated scenario where there is there is a dependence on the some kind of state which throws the reward. Okay, it's not like purely an i.i.d setting. Okay, so coming to the related work in 1987, in this work, the first algorithm was proposed by Anantram et al. And it was an index policy, and it matches the lower bound. So there was a so the upper bound of the policy that they have proposed matches the lower bound. So basically, it is an optimal policy that is proposed in this work. Very recently, around 2020, another work has emerged, which is an extension of an algorithm called KL-UCB. We will come to the details of KL-UCB later. So as of now, just think of this as an multi-amended algorithm. So they have used an extension of KL-UCB using sample mean of the reward, and we have considered the multiple play setting. So basically, multiple arms can be played together. All these are for the Markov chain model, Markovian model. But the problem with these two work is they have considered a single parameter family of transition matrix. So it's like, for example, when I have a two-state Markov chain, then to describe it fully, I need to have two parameters. Let's say I have two states, 0 and 1. So now if I want to describe this Markov chain completely, I need to know the parameter, let's say P01, which is the transition probability from state 0 to 1, and P10, which is the transition probability from state 1 to 0. So if I know these two parameters completely, then I'll be able to completely characterize the Markov chain. But in this case, they have considered it's a single parameter family. So instead of two parameters, they have considered that this Markov set of Markov chains, like set of arms. So each arm corresponds to a Markov chains, and all these set of Markov chains, they belong to a single parameter family. So there is an assumption that I can describe them using a single parameter, whatever may be the number of states. So that basically restricts the domain of Markov chains. In 2010, in Tekin et al., they have proposed this UCB-based policy using a sample mean reward. And in this case, they have found out logarithmic regret, which is the best regret that you can get in an order-wise manner. So you can get a logarithmic regret. However, the constants in front of the logarithm are not optimal. Okay. So in this work, they have not considered the single parameter family of transition matrix. So their work considers a more general class of Markov chains. However, since they have used a UCB-based policy, so although they are able to get logarithmic regret, but they are not able to match the constant with the lower bound. Okay. So, so in our work, what we have done is we have considered an extension of this KL-UCB for Markovian bandits, where instead of sample mean, we work with sample transition probability. Why? Because when we have a like let's say 2-state or 3-state Markov chain, then to completely characterize that Markov chain, I need a multi-parameter. I mean, it's not possible to work with a single parameter that may not be able to fully characterize that Markov chain. So instead of sample mean, which is single parameter, we work with sample transition probability. So we try to have an estimate of the transition probability from one state to another. And based on that, I try to extend the KL-UCB algorithm for that setting. Now, if you do that, then what we see is it outperforms this algorithm, which is the UCB based algorithm uh, for Markovian rewards. Okay, but the problem is it is bad for i.i.d. rewards, and i.i.d. rewards is a special case of Markovian bandits because under certain conditions, if you assume certain relationship between the transition probabilities of the Markov chain, then it becomes an i.i.d. And in that case, this our approach, this extension of KL-UCB for Markovian bandits don't work well because in this case, basically I am overdoing, right? Because we know that for i.i.d. rewards, there is sample mean is sufficient because for i.i.d. rewards, mean itself is good enough to characterize that process completely. So if I work with sample transition probability, then basically I'm overdoing and I'm trying to keep track of all the transition probabilities separately, and I'm not been able to exploit the relationship between the transition probabilities, which leads to the i.i.d. So therefore, here there is a need of coming up with an adaptiveness which can handle both Markovian as well as i.i.d. So to do that, what we do is we consider a total variation distance based test using the estimates of transition probability. So we kind of like have a we kind of store the estimates of transition probability and then we run a test. And this test, the answer of the test gives me basically tells me whether it's a i.i.d. bandit or a Markovian bandit. And if it is an i.i.d. bandit, we switch from sample transition probability to sample mean based KL-UCB. And if it is Markovian, we keep on running the sample transition probability. So the idea is I run an online test, and then test tells me whether my underlying dynamics is Markovian or i.i.d. If it is i.i.d., then I go for sample mean based KL-UCB. And if it is Markovian, truly Markovian, then I stick to sample transition probability based KL-UCB. After that, we found out the regret, upper bound on the regret, and then there are certain challenges in terms of invertibility of KL divergence because we are working in a multi-parameter setting. So what we do is we break our multi-parameter problem into smaller single parameter problems by using certain bounds. And then we also prove that the TV distance condition is satisfied infinitely often for the appropriate variant. Means when we prove that when our setting is truly Markovian, then the correct condition is satisfied infinitely often, and the incorrect condition is satisfied only a finite number of time, and hence then that does not have any impact in an asymptotic sense. Okay. So we consider no parameterization of the transition probability matrix, and the only assumption we do is irreducibility of Markov chain. And also we find out that our regret bound is lower than this work because instead of sample mean, we work with sample transition probability, which is a better way of doing it for truly Markovian arms. And also we use KL-UCB, that is a better algorithm in terms of confidence bound than UCB. So we will come to this KL-UCB, we will discuss in detail very soon. So before starting the problem formulation, is there any question? Okay. Okay, if not, so I'll now talk about the problem formulation. So in this case, what we are assuming is there is an arm I, and the arm I is we are considering as a two-state Markov chain. The rewards are generated from a two-state Markov chain that is given by 0, 1. I mean, it can be extended for multi-states also. That is there in the paper, but in this talk we will focus on a simpler setting, which is two-state Markov chain. So there are two states 0 and 1, and P01I is the transition probability from state 0 to 1, and P10I is the transition probability from state 1 to 0, and these are the self loops. So now reward from arm I in state S is given by Rs comma I, which is equal to S. Okay, so reward from arm I in state is S, and so what is the mean reward? Mean reward is given by this formula, and finally we get this. So pi I is the stationary probability of state, then what we get is pi I1, which is basically equal to this. So now you can easily see that mean reward is a function of P10I and P01I system well. Okay, and let's assume that mu star is basically the best arm, which is max over I mu I, and that is I'm assuming it to be equal to mu1, and delta I is the suboptimality gap. That means how much far you are from the optimal solution. So this is called suboptimality gap. Okay, now this is the definition of regret, as I was saying. So n mu1. So n mu1 is basically the oracle solution. Okay, so if you go back to here, mu1 is the max over I mu I. So that means if I have the knowledge of this mu I or the transition probabilities, then I'll be able to figure out which is the best arm, and I will always play that arm. Okay, so this is like an oracle solution. So if you do that, then n mu1 is the reward under the oracle solution, and this is the expected reward under the like chosen algorithm, your algorithm. Okay? And the difference between the mean rewards under the optimal policy and your policy basically constructs the regret of the policy alpha till time.
Question.
Yeah.
So can you please go back to the slide? Previous slide. Hello.
Yes,
Previous.
yes, I can hear.
Can you please? So here your the problem formulation. So here you are taking reward of arm I in status as S, right? So are you ensuring that the reward also follows the Markov distribution from this assumption?
No, I'm just saying that when you are in state I, state S, your reward is S, and then you make a jump.
But the state S is Markovian, right?
Yeah, this is a Markov. This state S is Markovian.
Correct. So that means that reward also is also evolving in the Markov chain, right?
Yes. So it is like this. When you are in state 0, you get reward 0, and then you make a jump. Either you in state 0 or you go to state 1 with this probability, and then when you next time if you pick, then you get reward 1 and so on.
Okay. Okay. Thank you.
Any other questions? So this is the regret, basically the policy alpha till time n. It is the difference between the mean rewards under optimal policy and the policy that we have. Okay, so now let's come to the bandit algorithms. First is never explode, that is like greedy. In this case, you choose arm with the greatest mean estimate. So these are the here I am talking about the evolution of bandit algorithm. So initially we had this greedy algorithm where you choose arm with the greatest mean estimate. And the problem with this algorithm is it may lock into a suboptimal arm, because it may happen that one arm, which is not really the best arm, but initially it gave you a good sample. And because of that, you tend to pick that arm again and again, and you don't go back to the best arm, originally best arm. So in this case, it may log it to a suboptimal arm, and then hence the regret becomes linear, which is not a good thing. I mean, linear regret means the learning is not happening. So we ideally want something which is sublinear, or actually we want something which is in logarithmic, because it has been proved that the best you can get is logarithmic. Second is forever explore, which is the epsilon greedy. So in this case, you explore with probability epsilon and exploit with the remaining probability. In this case also, the problem is your exploration probability is not changing with time. So even if let's say even if I have been able to find the best term after a large amount of time, still I will explore with a finite probability, and that is not good in terms of bandit performance. So it also gives you a linear. So the good thing to do, I mean, appropriate thing to do is basically epsilon t greedy, where the exploration probability epsilon t decays with time. And in fact, it gives you a logarithmic regret. But the problem with this algorithm is it requires the knowledge of mean reward to give you the good solution. So we need something which is giving us logarithmic regret, but without the knowledge of reward. So we want something like epsilon t greedy, where the exploration is gradually reduced. But in epsilon t greedy, there is some problem. So we need to come up with an algorithm which gives logarithmic regret, but does not require this. So that takes us to the lower bound, which says that the regret is logarithmic in time asymptotically. That is the lower bound. You cannot beat this lower bound. And if your algorithm is log n regret, then it is basically order optimum. At least you can say that order-wise, it is the optimum. Okay. So in epsilon greedy, the problem is we were not giving enough exploitation to the arm that is consistently performing better. Okay. So that's the problem with an epsilon greedy approach. There is if an arm is not pulled a lot of times, you are not allowing certain bonus towards it. So what we do is we add a upper confidence to the estimated mean that will overestimate the true mean with high probability. Okay. So this is the approach that we are going to take. So what we do is, instead of choosing based on the mean, instead of finding the greedy or epsilon greedy based on the mean, what we do is we add an upper confidence term which will overestimate the mean. And then if an arm is selected less number of times, I add a high bonus so that it gets chance to get it, so that eventually we pick the term. So that will act as an exploration term. And now if an arm is selected a lot of times, then we are very sure about the term. So we are not going to add a very high bonus. In that case, the exploration bonus will be less. So this is then called upper confidence bound. If you have a large TIT, I mean, if the arm has been chosen a lot of times, then you add a small confidence bound, small upper confidence. Or if an arm is selected less number of times, then you add a high upper confidence. And if you keep doing that, then eventually, because of your high exploration bonus or upper confidence to the uncertain arms, they will also get picked, and eventually it will ensure the right trade-off between exploration and exploration. Okay. So this is the algorithm which is known as this KL-UCB algorithm that we are talking. So we will refer to this as KL-UCB SM here. So this was proposed by Gary Weir et al. In 2011. So in this case, what they assume is, let's consider the setting that the reward from arm I is Bernoulli with parameter mu1. Okay. So we will use KL distance as an upper. So using KL distance, we will define our upper confidence bound. So what is the KL distance? So KL distance for two Bernoulli random variable with parameter A and B is given by this. Okay. In case of Bernoulli. So now we invoke that Chernoff bound, which says that if W1, W2, Wn is a sequence of Bernoulli random variable with mean mu, then the probability that the difference between mu hat and mu will be greater than epsilon is exponentially small. So what it says is, as n increases, as the sequence length increases, our mu hat and mu become closer to each other, and their deviation becoming very high becomes an exponentially small, which is exponential minus n, and then the KL distance between two Bernoulli random variable with parameter mu minus epsilon and mu. So this is known as Chernoff bound. Now, if I utilize this Chernoff bound for Bernoulli bandits, then I get the following algorithm, which says that whatever is your estimate of mean so far, so this is for the i.i.d setting. whatever is the estimate of mean so far, you come up with a number mu tilde, which is bigger than 1, so that this condition is satisfied. Okay. So we are looking for an upper confidence bound, which is basically a number which is bigger than mu hat, and then how much bigger? It is that is given by this. Okay. And then you find out the highest mu hat mu tilde which satisfies this condition, and then whoever is giving you the highest this index, you choose that arg. That's why there is a argmax over I. So argmax over I means whichever is giving you the highest this term, that term you select for the next term. Okay. So this is called KL-UCB, and it has been found to give you logarithmic. This algorithm gives you logarithmic regret. But this was originally proposed for an i.i.d. setting where the rewards are i.i.d. So now what we are going to do is we are going to take this algorithm and try to extend for the Markovian set, which has multiple parameters. Okay. So this has been proposed, proved to be asymptotically optimal for i.i.d. rewards. So when the rewards are i.i.d., this is known to be asymptotic. Okay, now let's come back to our original Markov chain problem. So we have a two-state Markov chain, and this is our mu I equal to P01I divided by P10I plus P. Now, if I want to like come up with an upper confidence bound like this mu hat for this, then what is the problem? Problem is we need to deal with two parameters that may be difficult to deal with, because generally, if you work with one parameter, it is easy, but now you need to deal with two parameters. So it will be like an upper confidence bound on some confidence bound on top of the estimate of P01I and some confidence bound on top of P10I. Okay. So there are two parameters instead of one parameter as in i.i.d. arms, and simultaneous confidence bound on both of them, the analysis becomes difficult. So what we do is we use confidence bound on the estimate of one parameter at a time. So what we do, when the state of the system is 0, then I consider upper confidence bound on this term and use the raw value of this term. And when the state of the system is 1, I use the upper confidence bound on P10I and use raw value of P0. Okay. So use upper confidence bound on the estimate of one parameter at a time and raw estimate of the other. Now, if I do that, we get this.
Is there any intuition behind that?
Sorry, your voice is breaking.
When you are using state 0, you are choosing the. Okay, so go back to the previous slide.
Yeah.
Yeah.
Yes.
Okay. So you are proposing that when you are in state 0, you will select the parameter P01I. I am interested to know that is there any intuition behind that?
So the intuition is the following. Basically, when you are in state 0, your reward distribution is Bernoulli with parameter P01I. Because with probability P01I, you go to state 1 and get reward 1. With the remaining probability, you get 0. When you are in state 1, you act according to Bernoulli with parameter like 1 minus P10I. Because with that probability, you get a 1, the remaining probability you get. So it's like earlier I was dealing with one Bernoulli, now I dealing with two Bernoullis. If you are in state 0, it is Bernoulli with parameter this. If you are in state 1, it is Bernoulli with parameter 1. So that's why we consider this state 0 and this.
Oh, okay.
Any other questions?
Okay, thanks.
Okay, so then the algorithm we get is this. So P10 hat I, this is the raw estimate I'm using, and this is P tilde, which is basically the upper confidence bound on this P101I. I mean, basically we are following the same sort of algorithm. Only thing is that I'm considering one parameter at a time and I'm using the raw value of the other. So here for P01I, I am considering an upper confidence bound, and for other term I am using as it is. Similarly, when my state is 1, then I am doing the reverse. So I am considering P01I the raw value of that hat, and then Q tilde I'm considering from this. So I'm considering an confidence bound on P10. Okay, so those things are basically, yeah. So in this case, I consider P01 upper confidence bound on that, and in state 1, I consider P10 estimate of that, and okay, and this gives us an easy way to deal with, because if we consider confidence bound on both the parameters together, then it becomes really hard to analyze. And then we choose whichever is, so for each of the arm, I calculate this, and then whichever gives me the highest value of the index, that I choose as the next arm. Okay, so if I do that, then what happens? Then for the truly Markovian rewards, as you can see that KL-UCB MC, this gives a lower regret. I mean, our algorithm performs better than KL-UCB SM, which is that sample mean. So sample mean based approach, we are able to outperform the sample mean based approach, and this is our performance. But for i.i.d. rewards, the situation reverses because our algorithm gives us higher peak. Why is that? Because for i.i.d. setting, which is a special case of Markovian setting, you already know that sample mean based approach is asymptotically optimal, that we have shown in this slide. Asymptotically optimal for i.i.d. reward. So if I am doing sample transition probability based, then basically I am like overdoing, and that gives us some reward because I am having an independent estimates of P01i and P10i, which is not required. If I just work with one estimate, that is fine because there is a dependence between these two. Okay. So now we are going to cater to this problem, that how can I get rid of this problem in the i.i.d. set. So for that, what I do is I come up with some algorithm which we called as TV KL-UCB. Basically, that is total variation KL-UCB. So i.i.d. rewards is a special case of Markovian rewards because when P01i plus P10i is equal to 1, then it becomes i. Now, KL-UCB SM is known to be optimal for i.i.d. rewards, but KL-UCB MC performs bad for i.i.d. So now you might be wondering from where this condition is coming. Just going back to the earlier question where I was explaining, so I go back to this. So from here, it is a Bernoulli with parameter P01i. From state 1, it is another Bernoulli with parameter 1 minus P10i. When both of them are same, then basically there is a single Bernoulli rather than two different Bernoullis, and hence from that I get this condition that P01i and P10i, sum of that is equal. Okay, so now this is the problem. This setting, only this like relationship is a problematic scenario. So what I do is I design a test for detecting whether my Markov chain is i.i.d. I mean whether my arms are i.i.d. or Markov. Okay. If I detect that they are i.i.d., then I switch to the sample mean based approach. And if I detect that if it is truly Markovian, which can be described using two parameters, then I go for our Markov chain based approach, sample transition probability based approach, where I use two parameters. And when I detect that it is i.i.d., I go to the KL-UCB, which has only one parameter. Okay, and we prove that actually this test is correct because the appropriate condition is satisfied infinitely often. So if I keep on running it, then infinitely often the appropriate condition satisfied for i.i.d., both i.i.d. and Markovian. And therefore the regret due to incurrent variant, because initially I might choose the wrong variant when the learning is still under progress, but the regret due to the incurrent variant will vanish in asymptotic sense. So now what is the TV distance? TV distance is given by this. If we have a two discrete probability distribution A and B with parameter A1, A2, AK, B1, B2, BK, then this TV distance, this is the formula. So now TV distance has been chosen for analytical convenience. It has been found that other distances such as Hellinger distance or some other distance, this also works. So here we have chosen TV distance. I mean, any other form of distance also may work. For example, Hellinger distance has been found to work. Okay, so what is the test for detecting i.i.d. or Markovian arm? This is given by this. Because for i.i.d. arms, P01i plus P10i is equal to 1. So what I do is I calculate the TV total variation distance with parameter P01 hat t and 1 minus P10 hat t. If I do that, then what should happen? If it is i.i.d., then with time, these two quantities will converge to the true value of P01 and P10, and hence this TV distance will converge to 0. That's what should happen ideally. So therefore, what I do is I compare this quantity with a decreasing sequence 1 by t to the power 1 by 4. And then when this is satisfied, I declare that arm as an i.i.d. And if it is not satisfied, then I declare that as a truly Markov. So this I'm comparing with a dynamic number, basically this 1 by 2 to the power 4. So the idea is as my learning increases, then gradually I become, this distance between these two quantities should become lesser and lesser. And eventually it should converge to 0, okay, for the i.i.d. case. So that is the motivation behind considering this test. Now, combining everything together, this gives us the algorithm. So what I do, I input, this is my input number of arms, I choose each arm once, and then this is the total variation distance for arm I. This is the total variation distance, and I am comparing with this parameter. Okay, if it is greater than, then I declare it as an truly Markovian, and if it is not, then I declare it for the i.i.d. scenario, and then then it becomes like this. So if the state of the arm is 0, then this is basically the sample transition probability kind of approach, where I consider and confidence bound on one parameter and keep the other parameter fixed based on the state of the system. And this is the sample mean based approach, where I consider an upper confidence bound on the estimated mean. Okay? So if this condition is satisfied, that means basically their TV distance is large, then I may not have an i.i.d. setting. If this condition is not satisfied, my TV distance is becoming smaller and smaller. So I can say that, okay, this is i.i.d. and then I can take up this approach. So this is the final algorithm for a two-state case. I mean, it can be extended for multi-states also. That extension is there in the main paper. So here I am talking about the two-state scenario. Okay. So this basically covers, this is the algorithm. So now we will talk about the regret analysis. That, okay, this is the algorithm. So what is the performance of that? So that can be captured through regret analysis, because that will give us that. So how much off we are from the optimal, how much off we are from the lower bound.
Question.
So that we are. Yeah.
So can you please explain the intuition behind choosing 1 by t minus 1 power 1 by 4? Why that?
So T1 by 4 basically this is used when I derive the regret bound, then this quantity gives us something like an let's say for the finiteness we need this term. If you go with something like 1/8, I mean anything less than 1 by 4 will work. But if you become more than 1 by 4, then the proof does not go through.
Okay.
So that's why, yeah, I mean it is not, yeah. So anything beyond this 1 by 4, 1 by 6, 1 by 8.
Thank you. Thank you.
Does it answer your question?
Yes. Yes. Thank you.
Anything else? Any other questions?
No.
Okay. So the regret upper bound, I will not go to the entire proof. I'll just talk about the proof sketch. So what we prove is, first we prove that the fraction of visit to states are close to the stationary probabilities. So here we will prove that the fraction of visit to states, like the fraction of time you are in state 0, that will be close to pi 0. Fraction of time I'm in state 1, that will be close to pi 1 for all the arms. The next result is estimates of transition probabilities are close to the true values. So the estimate of means the P10 I hat, P01 I hat, these will be close to the true value P01I. This is, I mean, if you run the system for a long time. And then the total variation distance condition, basically this condition. So for the i.i.d. arm, this condition, I mean, line number 8 will be satisfied, else will be satisfied infinitely often. And for truly Markovian case, this line number 4 will be satisfied infinitely. So that is the third result. The TV distance condition is satisfied infinitely often after a large time tau. So if you allow the system to run for a long time, then you can get this. And finally, the confidence bound on the transition probabilities for the optimal arm, estimate of transition probability for the optimal arm are close to the true value. So the optimal arm will be selected a lot of times, and finally the confidence bound will be close to the true values. Now combining everything together and choosing tau to be a function of C1 to be a function like C1 log n plus C2, where C1, C2 are functions of like transition probabilities for arm suboptimal arm I and optimal arm. Okay, then we get this. Finally, we get to this result that index of the suboptimal arm is not often greater than the index of the optimal arm. So most of the time, your optimal arm gives you a better index, and hence you end up choosing the optimal arm, and that basically tells you that if you run the system for a long enough time, you will be able to identify the best arm with high probability. Okay, so these are the results. The details you will be able to find out in the paper, and here with this kind of choices. So here you see that since tau is chosen as something like a log n, this actually gives us a logarithmic kind of behavior in the regret. Okay, and finally we come to this result. So our regret bound is something like this, that Rn by log n as n goes to infinity is can be shown in this. This is the result. It's not optimal, but it gives you a logarithmic. Similarly, for upper bound for other three combinations also can be right. So this is the combination that your optimal, suboptimal, both are Markovian, truly Markovian. There are three other combinations like truly Markovian optimal, i.i.d. suboptimal, i.i.d. optimal, truly Markovian suboptimal, and both i.i.d. So in case of both i.i.d, like when we have a full i.i.d setting, then upper bound matches the lower bound. So in this case, our algorithm is actually matching the lower bound, and it is optimal algorithm. But for other cases, there is a scope of improvement. But in simulations, we have seen that our algorithm performs much better than the earlier. So this is another result which says that if this condition is satisfied, then our algorithm is better than that UCB SM, that Tekin paper. So this is a mild condition, which this is, if this is satisfied, then it is better for truly Markovian case, and when i.i.d. suboptimal arm, it is always better. This also we have proved. And then these are some experimental results. So here you can see that this green one is our algorithm. Regret is much lower than other state-of-the-art algorithms, okay? And it is much lower than the other ones. And this is an experiment where we take this theorem. So in this theorem, we have considered this, that mean over I sigma is greater than equal to this. If this holds, then ours is better than the literature. But we allow the mean over I sigma I to be less than this. Then also, in simulations, we see that ours is still better. So upper bound on the regret is smaller than UCBSM, even when the condition on the theorem is. So here theoretically we have proven, but since but for the region which is not specified in the theory, we have done experiment, and then so here also the regret. So conclusions, KL-UCB, our algorithm detects the arm reward, whether it is Markovian or i.i.d, using a total variation distance based test. And then if it is a Markovian, then we can represent it using two parameters, P01I, P10I. For i.i.d, we need only one parameter, and then that motivates us to switch from sample transition probability based KL-UCB for the Markovian setting to sample mean based KL-UCB for the i.i.d setting. The regret upper bound matches the lower bound when i.i.d. arm reward. So for i.i.d. arm reward, ours is actually optimal, and it is a significant improvement over the state-of-the-art bandit algorithms that we have shown in the results, that the regret is much lower compared to the other algorithms. Okay, so in future we could look at something like usage of KL distance, which may be which may not be that easy compared to TP distance based solution. And another is this is also a problem, which is design of asymptotically optimal algorithm for truly Markovian arms, because ours is order wise it is optimal, it is giving logarithmic, but there is a chance of improving it further to make it asymptotically optimal. And the details of the proof and other stuff can be found out in this paper. For interest. So other research activities, I am also looking at other problems in my lab. That is, one is task scheduling policy for mobile edge computing system, where the various users are coming, tasks are coming at some IoT device, and then you need to decide where to execute it, whether you want to do it locally or you want to do it in the MEC server, mobile edge computing server, and that leads to some certain trade-off in terms of delay, power consumption. So those kind of trade-off can we address using machine learning. Second is this multi-arm bandit algorithm for beam tracking. So if an user in a next generation wireless system, when a user moves, then after the movement, the best. So you can throw beams towards this. You can beamform. You can do a beamforming or throw certain directed beams towards the user. So when the user has moved certain distance, the best beam changes. Now so it becomes a beam tracking problem. So now the question is, using multi-arm bandit sort of thing, can we formulate it as a multi-arm bandit problem and come up with an algorithm to do that? So we have a recent paper on this in WCNC. And another problem is this UAV placement in next generation wireless system. And also I'm working on some federated learning for systems. So that's it from my side. And these are some references, and thank you. I'll be happy to take questions.
Thank you, Professor Roy, for a wonderful talk. Are there any questions? So I think most of the questions were asked during the talk.
Okay.
So thank you
Anything
again.
in the chat?
There is a question about what Srinivas asked, key to the power 1 by 4.
Yeah.
That has been addressed. If there are no more questions, we can close this session.
Thank you.
Thank you, everyone.
Thank you
Have
for
a
the invitation.
great evening. Thank you.